Hello, we're in our final home stretch here. We're talking about solutions today, and it's starting in chapter 11. Posted our suggested practice problems, which we'll use in our next session. We have an exam 5 coming up, April 30th. So let's talk about concentrations and solutions, talk about how to analyze solutions, how to do some problems, some important properties of solutions, and using some of our knowledge in setting up stoichiometry solutions to problems. As I've been saying, that the summaries in the back of chapters are very good as a study guide. Here I'm posting my annotation of this chapter's summary at the end. Really helpful in after you read the chapter, pulling out important words and making some notes on them. Really good practice annotation. Helps you learn, retain useful information. So how do we describe solutions? They're always very important. Solutions all around us, starting our day, a lot of us, with the first solution that we make, and that's our cup of coffee. Solute, that's a substance that's dissolved in the solvent. The solvent's a major part of the solution itself. And then to quantitate and describe the solution, we talk about concentration of a solute. Of course, many solutions have multiple solutes in them, some just a single solute. And dilute, just as it sounds, relatively low concentration of the solute in the solution. We might have a more concentrated, these are all relative terms. And then finally, a saturated solution. That means we cannot put any more of the solute or dissolve any more of the solute into the solution at a given environmental condition. Mostly we're talking about temperature. And how do we quantitate? How do we quantitatively describe solutions? There's a few ways that we talk about in this chapter and do some calculations around. First is percentage, second is fraction, and third, molarity. So when we talk about concentration in percent terms, first we could talk about it mass per volume, most common way that we would describe percent concentration. And that's simply percent mass would be the solute divided by the mass of the solution times 100 to get mass percentage. And we'd describe that, we'd show that with mass over mass. Another way to present concentration in percentage would be by volume, and that would be the volume of the solute, and that would be, say we're making, as we see on the right there, our solution that we're going to clean the floor with. We would put some volume of the concentrate, the floor cleaner or the wax, into a final volume that is made up with water, and that would be by volume. So for instance, common we'd make up 5%. Bleach in water is a common way that we'd use cleaners. In fact, our bleach, Clorox bleach, is commonly 5% of that sodium hypochlorite is in there. Another way that we'd see it around us. Okay, so a cleaning solution, 2% by volume, ammonia and water. What's the volume of ammonia needed to prepare 10 liters? So we look at what information we're given and what we're asked. We're asked about the volume of the ammonia, the concentrated 2% ammonia, and we want to make up 10 liters of that. Okay, we'd write down we want the final volume to be 2%. I mean the final concentration of ammonia 2%. We want to know how much ammonia, solid ammonia in this case, per we want to make up 10 liters. So most important thing is to set up the problem, right? Set up the problem logically. What information do we have? What is the unknown? The volume of the solute is the unknown. We put that in its proper place. We want to put the percentage in terms of a decimal, and then now we're solving for volume. We do our arithmetic, do the algebra, we come up with 0.2 and use the proper number of significant digits. So 0.2 liters, it also equals 200 milliliters. And now an example of mass and volume. So that's another way to describe a concentration would be the mass over volume, as we said. So a very important liquid, if we need a saline solution, that is the saline solution. It's 0.9% sodium chloride, because that's the concentration of sodium chloride in our blood. So we'd, if we're asked about to describe this, so it's 0.9%. That would be the same as 0.9 grams of sodium chloride in 100 milliliters of water. So other things that are at some constant mass per volume, that's seawater is 3.5% sodium chloride per volume. And if you were ever near around the Dead Sea, an incredible phenomenon, the Dead Sea, that's about a half a mile below sea level, and it's a whopping 34% mass of sodium chloride per volume. The normal saline, 0.9%. How many grams of sodium chloride are needed to make a 0.50 liter of normal saline? So if you were on healthcare staff and need to make up some solution and need to sterilize it, this is a practical problem. So you'd write down, this is what we want to, that's our target, 0.90%, and it needs to be very accurate. You don't want to make a mistake with this, and we want to make a half a liter. Okay, so we know that that's what the 0.9% means. We need 0.90 grams per 100 mils, but we don't want 100 mils. We want 0.5 mils. So we would say 0.5 liters, and we need to make it up at this ratio right here. So we'd do this algebra, and we would then get, we need 4.5 grams of sodium chloride to make up that half liter. Okay, if we go very dilute solutions, if you're doing environmental analysis, this is the concentrations we talk about at part per million or part per billion. Might be some heavy metals or polychlorinated hydrocarbons or some kind of pesticides are at very low concentrations, so we need a good way to describe them, and this is how we describe them. And there's limits of what's acceptable, and let's see, we have part per million, part per billion, so these terms are part per billion would be the mass of the solute of the solution times 10 to the 9th. Now, so this is very low concentrations. We're talking about 1 part per million is 1 milligram, or 0.001 in 1,000 milliliters. Okay, so that comes out to 10 to the 6th or 1 milligram per liter. And a part per billion is a microgram, which is 0.0000001 gram per 1,000 milliliters, or 1,000 grams. So let's look at an example here. In a recent study, scientists have found samples of European wastewater treatment plant containing 45 micrograms, okay, that's 10 to the minus 6 grams of phthalates per liter of solution. What's the concentration in part per million, part per billion? Okay, so we are going to write down what we know. We know 45 micrograms is equal to 45 times 10 to the minus 6 grams. 1 liter is 1,000 grams. You need to know that. Each milliliter weighs 1 gram of water. Okay, so we set that up as shown there. The grams cancel out, and there we go, 0.045 parts per million. If we want to find out part per billion, okay, so a part per billion would be times 10 to the 9th, and that would be 45 parts per billion. And you should convince yourself for these calculations. If you see it for the first time, it looks a little daunting, but think this through, and we'll talk in the next session. Okay, so we talked about various ways of calculating and describing concentrations. Finally, we need to talk about molarity, because we talked a lot about moles. That is really the international accepted way to talk about amounts of matter is in moles. And molarity is simply moles of a solute per liter of solution. Just another way to describe concentrations. But now in terms of moles, not grams or volume. So it's grams per volume. So let's look at an example. Aqueous solution containing a volume of 9.41 liters contains 412.3 grams of dissolved potassium chloride. What's the molarity of the solution? Okay, so we know that grams, we need to make a calculation. We make the conversion to moles, which means we need the molar mass of that potassium chloride, which would convert it to moles. And then we have what volume it's in, so simply it would be that many moles over the volume. So you need to go through this thinking, the strategy of how to figure out how to get to the solution. Then we write down information we have. So from the periodic table, we'd be able to calculate, or you're given the molar mass of potassium chloride, shown there, grams per mole. Again, if we needed to calculate that, the molar mass, we just look at the atomic mass of potassium, atomic mass of chlorine is one of each. Just add those up and you'll get that molar mass. Okay, so we're making the conversion to moles right here. Grams cancel out, and we have that many moles. So we have 5.531 moles of potassium chloride. So we had 4 significant figures here, and we have 4 significant figures there. Okay, we have that many moles. Now, it is in this many liters, so that's the definition of molarity, moles per liter. And we come up with our answer. Now, right here we're given 3 significant figures, and that's why we're reporting a final answer in 3 significant figures. How many moles of HCl are there in 250 milliliters of 6 molar HCl, hydrochloric acid? Okay, so we know molar is the same as moles per liter. Moles per liter. Okay, so that's going to be important. This, we need to change this into liters to make this kind of calculation. Okay, so that's the thought process. Write down a few equations. So here we're changing the 250 into 0.250 liters. That's how many liters we have. And the molar is 6 moles per liter. So we multiply the moles per liter times the liters. We'll see the liters cancel out, and we'll get how many moles are there. 1.5. There's two significant figures. That's what we hold in our answer. Okay, so if we wanted to prepare a solution of a given molarity. You might say, okay, take a mole of something and add a liter of water. Well, it says not exactly. That's not exactly, because this mole of substance is going to take up some volume. And if we add that to the liter of water, that's going to be more than 1 liter. Right? So that's why we're saying it's not exactly. And we use a volumetric flask to make up solutions, because we put the solid in there first, and then we add the dissolving solution. If it's water or it's any other solvent, we'd add that right up to that line there, and then we know that this amount is in 1 liter of substance. If we started with a liter of the substance, we put it up to that line and then added the solvent, we'd be way over. The solution would not be a liter anymore, it'd be above the liter mark. So this is a volumetric flask. Okay, so how do we prepare a dilute solution from a concentrated one? Common thing that you might do in the lab, maybe you've done it already in the dilution. We'd say, okay, the moles initial have to be equal to moles in the end. So this is the equation that we use, the moles per volume, and then we're going to make a dilution, so we're going to increase the volume, and the moles will stay the same. Okay, so let's see, we have 25 mils of a 10.0 molar solution of potassium hydroxide. You add this to make 500 mils of a dilute solution. What's the molarity of it? So we're going to use that formula. The moles initial times volume equals the moles final times the molarity rather, time its volume. So this is the molarity, the initial molarity, the initial volume, and this is the final molarity and the final volume. So you'll note that these are inversely related. We increase one, we're going to decrease the other. So we write down what we have, can fill in the formula, what are we asking, and we could solve for the final volume, the final molarity, and that final molarity comes out to 0.500 moles of potassium hydroxide. If you start with a concentrated HCl solution of 12.0, you want to prepare 180 milliliters and of 1 molar. So we got to remember what these very important to remember. The M is moles per liter, mole per liter, and this is not in a unit that's consistent with this, so we're always going to have to be changing the milliliters. Just remember that that's not the same unit as this, so it needs to be, you might need to make a conversion there. Okay, so write down the formula, and what do we want to know? We want to know the volume of the concentrated HCl. So volume, so we're solving for the initial volume. How much do we need to make that final volume of 1 molar, and we need 180 milliliters of that. Okay, so we could set it up. In this case, we don't. If we keep this milliliters, it's okay because the molars cancel out, and we get 15 mils. Okay, another aspect of solutions. By the way, solutions. Way back when we talked about mixtures, a solution is a homogeneous mixture. It's a homogeneous mixture of the solute and the solvent, right? In a solution, we can't see those mixed, those homogeneous solutes that are in there. That's a homogeneous mixture. A saturated solution, if we keep adding and adding, go over the saturation, and it doesn't dissolve anymore, and there's solids sitting on the bottom. So that you might call a heterogeneous mixture, because we have solids that are not dissolved evenly or uniformly in the solvent. Okay, electrolyte, familiar with the name, with the word, electrolyte solution. We have those electrolytes in our sport drinks. We know it's very important to replace our electrolytes to stay healthy, not get cramps. And what exactly are electrolytes? Well, they're ionic compounds disassociated in water. So what we see right here is the common ionic compound, right? It's initially, as a solid, it's a crystalline lattice. But now we have water in here, water, universal solvent, that's going to disassociate these cations and anions, which are attracted to one another with ionic bonds. We know that that's electrostatic forces. And now the water kind of groups up and pulls apart, dissolving. This is the oxygen, which has a net negative. All right, so that's attracted to the positive of the, if we're talking about, let's just call it sodium chloride, that's the sodium being positive ion, and we have a negative dipole on the oxygen that's going to dissolve that, and the water, the other side of the water, the hydrogen, which is the positive dipole, will work to separate and kind of group and dissolve and dissociate the chloride ion. So that's what's happening there. Now, there's some ways that we need to think about this. So there's potassium bromide is a solid. If we dissolve that in water, we might show that as this, potassium bromide aqueous, AQ. We learned that. This is the solid. So the ions, we might show the ions together, but we know that really in the water these are dissolved as cations and anions. And we would represent that in what's called the ionic equation, which is showing the dissociation of the two ions, the cation and the anion. Similarly, here's hydrobromic acid, or hydrogen bromide. We're showing it here as a gas. If we dissolve that gas in water, we'll have an ionic equation shown on the bottom there. So if we talk about this at the molar level, let's take a mole per liter of magnesium chloride. Now, you should feel good about we're really using a lot of our knowledge that we've learned earlier. Magnesium, group 2 metal, so it's a magnesium 2+, and then we recall that chloride is a group 7 non-metal. So it's a -1, and that's why we have this is the ionic compound of +2 and 2 -1s forming that ionic substance, the ionic compound magnesium chloride. Now, when it's in water, it's going to dissolve to this magnesium 1 equivalent of magnesium 2+ and 2 equivalents of chloride ion. So if we had 1 mole of this substance, what are we going to have over here? Okay, so this dissolves. There's 1 mole of it here, and there's 2 moles of it there, so that's what we're going to get. We're going to get a solution containing 1 mole of magnesium ion and 2 moles of chloride ions. And there's some grilled cheese. What's the concentration of lithium ions and sulfate ions in a 3.5 molar solution of lithium sulfate? Okay, we want to write that down. Lithium sulfate, got to remember sulfate. Remember that's a polyatomic. It's a -2, 2 minus polyatomic. Lithiums were +1, group 1, and it's a polyatomic. And there we see it there. Okay, so we're asked, what's the concentration of lithium? So we have 3.5, we're told at this. Okay, so when it dissolves, this is the net ionic equation, it dissolves 2 for every 1 of these, right? So you should be able to think about this, apply an equation, or just kind of write this down. For every 1 there's going to be 2, so that means there's going to be 7 molar of the lithium ions and 3.5 of the sulfate. So anytime you're going through this, if you want to think about it more, take notes, you should be stopping the video. Grilled cheese again. Okay, write the ionic equation for the showing ions formed from ammonium sulfate, a phosphate dissolved in water. What's the concentration of ammonium and phosphate ions with this concentration of the solution? Okay, ammonium phosphate. I won't necessarily, I always have reference sheets or reference information. You won't have to remember off the top of your head what these look like, although it should be familiar. Ammonium is a polyatomic, phosphate a polyatomic also. You should note that this is an ionic compound. This is +1, and the phosphates are 3 minus. Okay, when they dissolve, there's 3 ammoniums because it's got a 3 down here. Phosphate is just 1 phosphate, and we got to put the charges there. And now, if we're starting with that concentration, well, for every one of these equivalent, we're going to get 3 of these and 1 of these. Okay, so it just goes to reason now. We're going to multiply this times 3 to get the ammonium concentration, and multiply by 1 to get the phosphate concentration, right? Okay. Alright, so that was looking at concentrations of electrolytes. Now there's some special properties of ions in solution we need to know about, and these are called colligative properties. They're important because these properties, they do not depend on the type of particle, or in this case we've been talking about ions, that are in solution, only the number of those particles dissolved in solution. So there's 3 that we'll mention here, and some examples of how they're important examples that we know, phenomenon that we know around us. So freezing point depression. Why do they put down some kind of salt solution or salt solids on the roads when we expect things to be icy? Well, here's a nice graph of freezing point, that is the point that things turn to ice, and solute concentration of the aqueous solution. You can see that as we increase the concentration here in moles per kilogram, so that's another kind of concentration we might be thinking about. Anyway, we have the 3 that increasing the amount decreases the temperature that the ice forms. So that's important. So we know that without any of this salt or substance, freezing point is 0 degrees C. As we keep adding more of that, we are decreasing. It's decreasing the freezing point, which is a good thing, because now if we add 1 equivalent here, then the ice on the roads won't freeze until it's less than 0, somewhere around -2 to -5 degrees. It'll keep increasing. We see that the more concentration, the lower the freezing point is. We could also look at the difference here. So with sucrose, it's got this kind of freezing point depression, a little more steeper depression with sodium chloride, and even a steeper more with calcium chloride. So if you were asked, what's your hypothesis why this is happening, you could think about it for a while. You could probably come up with an answer based on what we just talked about. If we look at the differences here, if we dissolve sucrose in water, we're going to get, this is a molecular compound. It's not going to break up into ions. Sodium chloride is going to break up into 2 ions, and calcium chloride is going to break up into 3 ions. Okay, so that would explain a bit that we have more ions present. The higher concentrations of ions, the lower the freezing point is, or the better the freezing point depression is. Okay, so that's our sucrose. Dissolves in water, just 1 molecule of sucrose, 1 mole to mole. If we dissolve the salt sodium chloride, we get 2 moles, and dissolving the calcium chloride, we get 3 moles. So you can see we have more moles of particles in with the calcium chloride. So that's why what we put on the roads nowadays is calcium chloride. It might be a mix of calcium chloride and sodium chloride, depending on the prices and costs of things and what the states might have in their inventory. But you could see that calcium chloride would be effective at decreasing the melting point. Okay, boiling point's the other one common thing that we use to adjust boiling point is antifreeze. We put antifreeze in our engines so that we don't have the engine overheating as easily. So that's our water there. We see freezes at 0 and boils at 100. Where we add some concentration, some of that ethylene glycol, which is antifreeze, we will broaden the spectrum here. It won't boil until 106 degrees C, and it won't freeze until way down to -45 degrees C, which so that's by adding antifreeze, or replacing the majority of our water with antifreeze in our radiators, in our vehicles. look at a couple examples. Freezing point of a solution of sodium carbonate, or 2 molar of aluminum chloride. So we're looking for the concentration of ions. Which one has a higher concentration of ions or particles? So this one, the sodium carbonate, dissolves to 3 equivalents. So if we add up that, we're going to get to 9. And for the aluminum chloride, we are going to get the 2 molar goes to 8. So the winner is the sodium carbonate. That will lower the freezing point a little more. Alright, one other phenomenon that relies on colligative properties is osmotic pressure. Osmotic pressure. So osmotic pressure is the way that water is going to move across a semi-permeable membrane. So the water, in which the water can pass, but the particles or ions cannot, molecules or ions cannot pass through, similar to our cells in our body, and that's what's shown here. Exterior of a cell, interior of the cell. And we balance our osmotic pressure, or keeping our cells with enough water, by adjusting the presence of electrolytes inside and outside of cells. And that adjustment to maintain the proper osmotic pressure is by the concentrations of ions. So here's a demonstration here. On one side, the left side, we have water, which is shown by those Mickey Mouse-like little diagrams there. And the electrolytes, presumably it would be sodium, the purple, and chloride, the green. Now, if we let this sit and come to equilibrium, and only water can pass through the membrane, which is right here. It's the semi-permeable membrane that only will allow water to go back and forth. Think about what you'd predict is going to happen here. Which way is the water going to flow? Well, if you said this way, you're wrong. It's going to be going this way to try to make this more dilute. So the water is going to move that way to make that dilute. It's going to increase it so that the if we envision a town A and B that are at equilibrium, they're about the same populations, and businesses are about the same, and the populations are fine. If there's a factory in town A, it says is now hiring, the populations will change. So we could think of that as another way that we will show equilibrium being established. Osmotic pressure, very important to maintaining the pressure and ultimately blood pressure in our bodies. And you can see how what we remember discussing was shown there. This is intermolecular forces in action here, with the chloride ion around water and the sodium ion are also around water, but the opposite dipole of the water molecule. So good. hypertonic solution in which water is moving out of the cell to equilibrate its surroundings, we'd have the cell being bursting, and if water moves out of the cell, we'd in a hypertonic solution, we'd have a cell collapsing. So isotonic would be established equilibrium, and if we go back a bit, that is a saline solution concentration of 0.9% sodium chloride would be isotonic, and that's really important in maintaining our blood pressure. Okay, let's take a look at a question here. We have a 1 molar aqueous sodium chloride solution and a 1 molar aqueous calcium chloride solution separated by a semi-permeable membrane. Which solution has the higher osmotic pressure? So this is the semi-permeable membrane in which only water can move back and forth. Right, so we have these concentrations of these ions. We could call them electrolytes, so they're not, of course, as sodium chloride, but sodium +1 and chloride minus, calcium 2+, and 2 chlorides -1. So that's important to remember. We have dissociation of these substances. If you write the ionic equation, recall, let's see, so will the water flow toward the sodium chloride or toward the calcium chloride? So what we want to do is think about the concentrations of the particles, and in case the particles are the ions, what's the molarity of the ions? So in this case, we have sodium chloride, we have a mole of sodium and a mole of chloride, so we have 2 moles of solute. Over here we'd have 1 and +2, we have 3 moles of solute. Okay, so you should have gone through, reason that with me there. And then we could think about which way is the water going to move to reach some kind of equilibrium. Okay, so that's the higher concentration. So the water wants to move to equilibrate the osmotic pressure, which is created by the concentrations of the particles. So the water wants to move to dilute this side. It's more concentrated. So the water will be moving to the right, to the calcium chloride, to reach an equilibrium. So in summary, colligative properties, they don't depend on the type of molecule, the type of particle, or type of ions, or type of, in this case of sucrose, that was a molecule, dissolved molecule, and particles and or ions, so we group them under the general word particles. It affects these 3 phenomena: freezing point depression, boiling point elevation, and osmotic pressure. 3 important phenomenon around us. We saw some nice examples of them. Okay, reaction to solution. We'll mention a little bit about this. It goes back from previously we talked about types of reactions, so you should be familiar with these words here. So here's a nice little reaction happening here. Probably involves lead. So we're pouring a solution in here, and bam, something's happening here. And that looks like a solid being produced from 2 liquids in. Okay, 2 solutions combine to form a solid product. That's a precipitation reaction. And here's, let's look at one here. It's a molecular equation that's showing everything. It's written completely out. We have silver nitrate reacting with potassium chloride, okay, all in water, aqueous, and we have the formation of silver chloride solid, and we have potassium nitrate aqueous. Now, if we want to write out the complete ionic equation, we do this, because we know that aqueous means we have these ions floating around, not really floating around in this form, but as ions. So you should be able to see that now we know that the solid is formed, so that we do write as a compound. But these are also in as ions, because we have this right here, aqueous. If we wanted to write the net ionic equation of what really happened in this reaction, we boil it down to just this. Aqueous silver ion combined with aqueous chloride ion to form silver chloride solid. Now, how do you predict these kind of things? Well, you don't have to remember and be able to predict them. It's all shown on a nice little table, a solubility table. You might have to read this in our next exam, and that's not too difficult. It's just say, here's the chloride, and when chloride is in solution with silver right here, go over and we see that it is blue. What does blue mean? Blue means it's insoluble, which means it's precipitating, and that's exactly what we just saw. If we mix nitrate with, say, there's potassium here, there's potassium, which happened in the reaction also with potassium, nitrate and potassium, put those together in water, and what does that mean? It's soluble. That's why they didn't precipitate. Right, so that's the way that we read a solubility table. Now, there's also an aspect to this also. It involves a little bit of concentration. If we have too low a concentration of one or the other of these, we might not see the precipitation. It might form, but it might be hard to see. We have to increase the concentration or use some other method of seeing the precipitation. For instance, it might be a little cloudy instead of showing that real heavy precipitate in the case of a dilute mixture. Another thing when we're talking about solutions is acid and base. We'll just mention a little bit. Acids and bases, they when they combine, we call this a neutralization. So an acid and a base neutralizes to water and a salt. So here's an example. Here's HCl, hydrochloric acid, and mixing it with a base, which is hydroxide ion, and this H is the acid and the base. These come together to form water, and the other two things come together to form a salt. But you see that this salt, if we looked on the solubility table, we'd see that this is not a insoluble salt, so they're just floating around as ions. But this is a neutralization reaction because the acid, which is the H, and the base combine to form water. A single replacement, you might remember single replacements. Well, that happens in aqueous solutions, and we'll just mention it here again. Here's copper and silver nitrate. If they combine, we see that molecular, everything written out there, but we might note that what happened here. Well, the copper now suddenly is in solution, as shown by this right here, and this silver that was in solution here, when it combined here, now it's suddenly a solid. And we might see that in this little picture here. So this is the copper, and it's in right here, the silver nitrates in solution. Well, with a little time, then we see the silver plating out on that copper, which that's that reaction. It's a single displacement reaction, which you should remember. When we have an element, metal usually, and then it displaces the other metal, it's a single replacement reaction. Here we're calling it a metal displacement reaction. And there's the net ionic reaction. So I will want you to be able to see this, figure out, okay, this is the net ionic equation. We don't describe the things that are called spectator ions and don't do anything. They just kind of stay in solution. In this case, it's the nitrate, right? The nitrate is not doing anything. It's staying aqueous. So we drop that out of the equation. All right, so we just looked at a few important solution reactions: precipitation, acid neutralization, and metal displacement. And this is a nice summary table. That you can go back and look at. Finally, just to mention solution stoichiometry. Stoichiometry means we're looking at an equation and talking about quantitatively what's going on, and we do that by changing things into moles. We just look at a couple of examples here. Silver chloride reacts with this net ionic equation. Based on this, how many grams of silver chloride precipitate could be produced when 10.0 mils of a solution of 0.0023 molar chloride ion reacts with excess silver ion. Okay, so this excess means we don't have to consider, we have plenty of this, so we're really just concerned with, we're given an amount of this, and we're going to figure out how much exactly, how many moles of that exactly by using this information. Alright, so we have the molarity of the chloride, and we have the volume of it. Molarity, remember, is moles per volume. So we could figure out the moles of chloride. And then convert the amount of this formed, which is, look here, it's a 1-to-1 relation. So if we have 1 mole of this, we're going to get 1 mole of that. Well, whatever the moles we get of chloride is going to get the moles of this, because we have an excess of this. And then we convert from moles to grams, because we're asked about grams. So let's see the numbers here, and you could stop this and look at it a little more closely. And you see you're setting up, you're doing dimensional analysis, you figure out the amount of moles of chloride, and finally go to grams of silver chloride, and we do that with molar mass. So you're going to have to get the molar mass of silver chloride. We add up from the periodic table the atomic mass of the silver and the chloride, and that's written right there, 143.32 grams per mole. And we will come up with that many grams of silver chloride formed from this amount of the chloride ions. So this is a good example. I will not ask you anything more complicated than something like this. The next example is a little more complicated, interesting to look at. So gravimetric just means we used mass, which we just did. So here's, and we saw this, we we saw this example a little earlier, lead plus plus iodide ion, and that's gonna form this crazy yellow stuff. Really cool little reaction that you could do. Maybe you did it in the lab, maybe we'll do it. Lead plus iodide forms this lead iodide solid that's brilliant yellow, and we can figure out the mass of that, and we could do some calculations around how how efficient is that reaction. There's another example you could look at on your own. We'll go over some of these examples when we're together in person. Okay, we're going to stop here, and we'll look forward to getting together next time in person. Make sure you go through this, do those practice problems, please, and we'll talk about this next time.